Swayam Prabha. Digital India. Educated India.
Sir, you can start, sir. We are live.
Good evening to all participants of the NPTEL course Fundamentals of Theoretical and Experimental Aerodynamics. We are very glad that you have been participating very actively in this course, and we have been receiving a lot of questions, queries on a regular basis. And we have addressed some of them from time to time, but I thought that I would take up quite a few of those questions and address them in this second live session scheduled from 4 p.m. on 21st March 2022. This is our team comprising of myself and the course TA students, Mr. Arpit Mishra and Mr. Arjun Garva. We are all from IIT Khanpur. So let's move on to the questions. There's a question from Amit where he asks that can you please explain why first law is not written for open systems? So he's referring to the first law of thermodynamics, of course. And let us address the question. Refer to the first law from a closed system perspective. So it's an appropriate question what he's raising. So when we look at it from a closed system perspective, so it has a closed boundary, it has a certain amount of matter contained in it, and the gas, the working fluid which is contained within it, it comprises of molecules, atoms, which are in a state of constant random motion. And by virtue of that, it has a certain amount of energy. Let's call it as internal energy. And per unit mass, it becomes specific internal energy. So that would be represented as as E, sorry. And then there could be a small change in this energy if there is exchange of heat or work with the system from the boundary, or the heat transfer could be even within. So in such situations, there could be a certain heat exchange given by del Q, a certain work exchange given by del W, and then there is a change, there's a corresponding change in the internal energy. And according to the statement of first law, by virtue of energy conservation, that is how they balance. Now, addressing the question, we move on and we say that we can write it for an open system as well. It's not confined to a closed system only. And then what we can look at is a kind of a control volume that we define in the surrounding. The surrounding, for example, could be a fluid medium, which is in a state of motion. And some fluid moves into the control volume through the control volume boundaries and move out as well. And as they move through the control volume, there could be heat and work exchanges. In such a situation, we basically talk about a rate equation. So it now becomes a rate of heat added to fluid inside control volume from surroundings, again rate of work done on fluid inside the control volume, and then based on those rates, you have a rate of change of energy of the fluid as it flows through the control volume. So we can very much apply it in this sense, and then it becomes an open system application of energy equation. And here we have quoted a specific form of that energy equation. In integral form, we have expressed the energy equation for a situation of steady inviscid flow without body forces. So that's how you could go ahead and apply the first law equation in case of an open system as well. Let's move on to the next question from Rajat. He says that, can you explain in detail steps how exactly you obtain this expression, which is basically the energy conservation equation. And he wants to know that how from the integral form of conservation equation, we arrive at this form, which basically talks about conservation of the stagnation enthalpy. So for doing that, we are actually referring to how stagnation enthalpy remains conserved across a normal shock. And for enveloping the normal shock, we had defined a one-dimensional control volume of cross-sectional area A, and then we defined two stations, 1 and 2 respectively, at the inflow and the outflow directions or stations of the control volume. And we also defined the state of the fluid at the two stations. And based on what we just discussed in the previous slide, we could write down the energy equation in this form, the energy conservation equation in this form. And we are ignoring the heating term, and therefore we are talking about an adiabatic condition in this case. Therefore, now we have to basically apply this integral form of the equation to the control volume. Based on the fluxes, we have to work out the equation for the energy conservation. So how we do it is we take the terms in the integrals and try to work it out for the two stations, because those are the two stations through which the flux exchanges take place. The other two surfaces are not participating in any kind of flux exchange, because it's basically a one-dimensional flow that we are talking about. Remember that the unit normal, which points out of this face, is opposite to the flow direction, while the unit normal, which points out from this face, is along the flow direction. And therefore, when you do a dot product between the velocity and the area vector, then the signs accordingly come up. So that is what matters over here. When you do a VDS, the ds basically stands for the area vector, and then you have the scalar form of it, that is a into the n, that is the unit normal, which is pointing out of that area. And therefore, if they're aligned in the same direction, this produces a positive term, otherwise it produces a negative term. So going by that, you would get a negative contribution at the inflow and a positive contribution at the outflow. Similar things happen for the pressure-based term. And additionally, it has a negative sign, so that sign comes up over here. Once you are done with this, which is the most important step, you can rearrange the terms and put them in this form. And using the same control volume based approach, we can show that the continuity equation in this case, which is basically corresponding to a compressible flow situation where density changes from point to point, the product of density and the velocity remains conserved. So the continuity equation, how do we use it here in this equation? We divide the left-hand side of the energy equation by the expression ρ1 u1 and the right-hand side of the energy equation by ρ2 u2. Once you do that, it comes to this form. And then from the definition of enthalpy, we know it is equal to E plus PV, or P by rho. And that is what you have here. That means this is enthalpy at station 1, this is enthalpy at station 2, and those are static enthalpies, remember. This is the dynamic part, which adds on to it, and therefore what you essentially have over here is stagnation enthalpy. And the statement basically indicates that the stagnation enthalpy is conserved between the 1 and 2 locations. That means there's no jump in stagnation enthalpy as you move across the shock. So I hope that question is addressed. Let's move on to the next question from Sunil, where he says that V is the velocity of flow here. So he's talking about propagation of the flow as well as propagation of pressure waves, and if there is a shock formation, how do they work out? So the shock phenomena is related to wave speed, and u plus a is the wave speed locally. Fluid local velocity, that is u, is not greater than a. This understanding is correct. What reflects back is the pressure wave at speed a or the fluid reflects back at speed a. So, well, let's try to address the query. To begin with, we'll keep the wave diagram for 1D Euler equation here so that we can recall what we had discussed in that context, because it does have a significance over here. To begin answering this question, v is the flow velocity, certainly. Now, if you simplify the problem and you consider it as a one-dimensional flow problem, it can be represented as u, because v only has the u component in this case. In the case of supersonic flow, of course, this flow velocity u is greater than the sonic speed, the local sonic speed a. If you look at it from the characteristics point of view, you have learned from the wave diagram, which is this, for 1D Euler equations, which actually came up in a later lecture after this lecture 33, that there are three different characteristics. So dx dt equal to u minus a equal to u and u plus a. These were the three characteristics that we have learned about in a later lecture. And these are all associated with 1D inviscid compressible flow moving with velocity u. Now, these characteristics are associated with wave propagation, mind it. And not all of them travel at the same velocity as the flow. So the flow moves, that is a physical movement of the medium. Along with that, perturbations are propagating in the form of waves. These characteristics are talking about that. That is evident from the presence of three different characteristics for one flow velocity, because you only have one velocity, but there are three sets of ripples as though, which are moving through the medium, which are conveyed through the concept of characteristics. So what information are these waves propagating? Let's try to figure out. Now the wave front dx dt equal to u, or otherwise putting it as dx equal to u dt, they are the same as the path lines. Therefore, the family of waves given by dx dt equal to u, they travel along with the fluid. So there is a wave which is propagating along with the flow. Now, what signal does it propagate? It propagates the signal of entropy. So these waves are called as entropy waves. We are left with two more. So two families of characteristics, one with the dx dt equal to u minus a, the other with u plus a. So we already saw that dx equal to u dt corresponds to the travel with the local flow speed. Now, if it is u plus a, it corresponds to a travel at the local flow speed plus the local speed of sound. You can better call it even velocity, because that has the directional sense as well. Whereas u minus a corresponds to travel at the local flow speed minus the local speed of sound. In either case, the wave speed is the speed of sound relative to the flow. So there is apparently a sound propagation relative to the flow, either along the flow direction or opposite to it. So such waves are called as acoustic waves. The acoustic waves define a domain of dependence and range of influence, which you have learned about, and we can very easily show it in the xt plane. These are essentially pressure waves. Now, when we mention about disturbances propagating through the field, they do so through the acoustic waves. The disturbances caused due to presence of an obstacle propagate. It is not the flow which reflects back. So this is the answer to the last part of your question. I hope your queries are clarified. Next question from Rajat. Can you please share more detailed reasoning why with decreasing Mach number, theta, or the wave angle decreases, and lower limit of Mach number for which shock remains to attach, or remains attached, I would take it that way. Now, we of course have to recall the theta beta m relation in order to answer your question, where this equation basically connects the upstream Mach number, the compression angle theta, and the wave angle beta. Now, if we recall about the theta beta m diagram that we had discussed in this lecture, then it looks like this. So theta is along the x-axis, beta is along the y-axis, and we plot the curves for different values of m1. We find that as the m1 becomes larger, the envelope gets bigger. And you may recall that also for each one of these Mach numbers, you can actually divide the range along beta into a weak shock solution and a strong shock solution. And based on that, the downstream Mach number will accordingly remain supersonic or will turn subsonic, depending on whether it's a weak shock solution or a strong shock solution, respectively. Again, you notice that as the Mach number gets larger, the maximum theta for which you can still have an attached shock keeps increasing. Now, these behaviors are all coming from your flow kinematics and the conservation equations which have been plugged in suitably. Now, if you look into the detailed derivation of this equation, you can, of course, refer to some of the standard textbooks and look through the different steps for the derivation. But interestingly, it's all conveyed here through these graphs, what we are trying to say. That means the basic lesson is that as the Mach number reduces, the maximum compression that it can sustain to have an attached oblique shock keeps reducing. That's one of the important learnings from this plot. So we can actually observe these things happening when we perform physical experiments in wind tunnels. If you try to do experiments with, say, a wedge model inserted in the test section of a wind tunnel, you would find that if the compression angle is too high, then if your wind tunnel test section Mach number is not all that high, such that you could actually have an attached shock, you'll see that the shock gets detached from the wedge. Whereas for the same Mach number, if you now insert a slender one, you will see immediately that the shock gets attached to it. So this is how we would like to address your question. You have one more where you're saying that can we say that when angle beta tends to 90 degrees, we approach normal shock situation hypothetically because we are increasing beta. With higher beta, we get a strong shock solution, and the strongest shock would be a normal shock as the limiting case. Well, yeah, conceptually, that is what it is. And we are actually showing the theta beta m plot once again with some more detailing. And some of these things we have, of course, mentioned earlier, that the strong shock part makes the flow subsonic behind the shock, while the weak shock part keeps it supersonic. And then, as you said, that yes, of course, as you approach beta equal to 90 degrees condition, then you are essentially approaching the normal shock situation. We move on to the next query, that is from Yash Patel. This is on a different problem domain. Till before this question, we have been mainly talking about compressible flows, application of energy equation to shock waves. We have also dealt with the theta beta m relation, etc. But this is a question related to finite wing theory. And there we essentially discussed within the domain of incompressible flows. So Yash has a question on Biot-Savart's law, and he is asking that the direction of velocity due to vortex strength will be perpendicular and into the plane, as dl and r vector both are in same plane, and cross product of them will give the velocity into and perpendicular to the plane. Well, assuming that this is a question and not a statement, let us try to address the question that Yash has raised. So we are just referring back to this figure, which is basically taken from one of the lectures, where we do see the vortex filament here and the associated circulation. And you have a field point P, which is at a distance indicated by this displacement vector. And then we are talking about the velocity which is induced at that field point P. Now, you are absolutely right. Let us say that we are having the dl pointing along the y direction and the r is along the x direction. So following the right hand rule, when you take a cross product, that is the dl cross r, which we need to do over here, then obviously that cross product will produce a vector which is going to point along the negative z direction. So that is how the vector will point, and that's of course going to be perpendicular to the plane containing the dl and r and downwards. So that gives the velocity direction into and perpendicular to the plane, which you have rightly mentioned. So whatever you have stated is correct. Next question from Rajat. I'm not able to understand how equating downwash and upwash to 0 ensures that the wing surface becomes the flow streamline. Can you please explain this with a physical and mathematical description? Well, we just recall that in the context of the finite wing theory, when we had discussed about downwash, we simultaneously also discussed about upwash, but we said that downwash is what the wing sees and upwash is going to occur at a distance. So when we perform the calculations on the wing surface, it's essentially the downwash only. But then it may not be a single wing which we may be looking at all the time. So there could be situations where you have tandem wings or multiple wings in proximity. So in that case, it's not downwash alone always. It could be a mix of upwash and downwash due to interactions between different wing surfaces. So that's the general picture. Apart from that, we always need to keep in mind that we need to account for the effect of the free stream and the angle at which it is coming and impinging on the lifting surface. So recalling that upwash is associated with the upward movement of the flow and the downwash is associated with the downward movement of the flow with respect to your reference surface, which is in general a wing surface. Now, if you take a sum total effect of the free stream and let's say the upwash downwash combination, which becomes more relevant in a multi-wing situation, the sum total effects become 0 at the wing surface. If that really happens, then the wing surface becomes a streamline of the flow. And that basically means that the flow would move tangentially along the wing surface. And all this is basically happening within the perspective of potential flow. And if you are doing that, then there's no possibility of flow separation, where flow ceases to move tangentially to the wing surface if flow separation occurs at all. So ruling such possibilities out, you can clearly state that yes, sum total effect of the free stream and upward downwash effects, if they become 0, then certainly the wing surface becomes a streamline of the flow, because the flow in an overall sense follows the wing surface. That's basically the idea. Moving on to the next question, that's from Topiwala Adit Dharmesh. We know that most of the fluid and flow properties are strong functions of temperature. In case of high enthalpy flow, it is good to incorporate the non-equilibrium flow model. My question is, if we consider two temperature models, kinetic model could be, along with the non-equilibrium model, what major differences we might expect with respect to the calorically perfect gas model? Okay, so this is a fairly complex question, and this is quite advanced material, which could be best addressed in a complete course on hypersonic and high temperature gas dynamics. But since our course is of a very introductory nature, I'm just trying to address the question from such a perspective. So, Adit, you must have done quite a bit of reading and learning in this area. So that comes out clearly from your question. But keeping in mind that there could be many students who are not familiar to such depth in this area, I would first like to mention this book, which is very useful, which you may be already familiar with, but this is for other students also for information. So that's the book by J.D. Anderson, Hypersonic and High Temperature Gas Dynamics, which is a very useful reading material if you really want to go deeper into hypersonic flows. And whatever you have stated, it certainly makes sense. That is, you would have to incorporate such models in order to tackle high enthalpy, high speed flows. So non-equilibrium often comes into picture in such cases because the flow times would be much smaller compared to the times which are the characteristic times required for completion of chemical reactions, and therefore you could have non-equilibrium situations. And then, of course, accounting for them is very, very important. Also, we need to understand the aspects of equilibrium, frozen flow, non-equilibrium flow, all in a very detailed manner in order to address these questions. But if I take your question broadly in this form, that if we look at these kind of situations, high enthalpy situations from a perfect gas point, calorically perfect gas point of view, and a reacting flow, chemically reacting flow point of view, then broadly where would the differences manifest? So taking your question from that point of view, a very interesting thing that one may notice comes from the study of bluff body flows in these kind of Mach number ranges, where if you look closely to the nose portion of such a configuration, you will see the stagnation point region, which is going to broadly have a equilibrium kind of flow behavior. And then there would be regions where the flow is near frozen and also non-equilibrium flow. So it is a complex regime that we are talking about. And from the differences in the manifestations, a very major difference which comes up, which is worth mentioning, is if you look at the shock standoff distance, there could be significant differences between a shock wave structure which is predicted based on a constant gamma. That is typically the calorically perfect gas model that we are talking about here on one hand, and a chemically reacting flow on the other. So you find that from this diagram, which is taken from this reference, the shock standoff is higher. That means the shock stands out at a larger distance for a calorically perfect gas model than a chemically reacting flow model. So the shock comes much closer to the body if you account for the chemical reactions. And then when it comes to chemical reactions, of course, you would have to account for the non-equilibrium effects because of the hypersonic regime, where the flow is moving way too fast so that chemical equilibrium is actually achieved. So shock standoff distance difference is one of the major issues which you can explore further. If that happens, then as you can understand, that would also create differences in the pressure distribution on the body surface. And there are several interesting differences which you may have already come across, but I'm just mentioning here. You may have looked at the density ratio, where when you assume calorically perfect gas, we have already seen that in the limit m infinity tending to infinity, the ratio goes to 6 when you assume gamma equal to 1.4. But when you account for chemical reactions, it goes much higher, about 4 times higher, to ratios of the order of 22. So you can see very well that there are major differences coming up because of the hypersonic effects. I have also mentioned one or two points which actually came from studies on the space shuttle, which of course is no longer in service, but during its service, these things were noticed in the earlier part of the life cycle. So when they did high temperature equilibrium air thermodynamic property based calculations for the space shuttle, they had an unexpected result. So an unexpected effect of high temperature flow on the space shuttle was observed during the flights, and it indicated a much higher pitching moment at hypersonic speeds than was predicted based on this model. This required the body flap deflection for trim to be more than twice than that was predicted. So this discrepancy is considered to be one of the few major anomalies between design predictions and actual flight performance for the shuttle. And the opinion of the scientists was the discrepancy was caused by the effects of a chemically reacting shock layer. So they did not account for it earlier, and then it led to grossly different pitching moment acting on the vehicle. So the actual pitching moment was much higher. For chemically reacting flow, the pressures are slightly higher on the forward part of the shuttle and slightly lower on the rearward part compared to the equilibrium air thermodynamic case. This results in a more positive pitching moment. And because the moment is the integral effect of the pressure through a moment arm, a slight change in pressure can substantially affect the moment. This is again a very important point. So we need to understand that accounting for the chemically reacting flow may produce minuscule changes in pressure over the body surface, but when it comes to moment calculations, because the moment arm is playing a major role in leveraging small changes and making them amplified, therefore there could be ultimately significant changes. I remember having seen another question from you which was more advanced on drag predictions for block body flows under different modeling situations. You could probably review from these angles and try to find some answer to those questions because you already have reviewed this material quite thoroughly. Thank you for such thought-provoking questions. Next question from Rajat. Why there is a reduction in drag coefficient after sonic Mach number as shown in the CD versus Mach number graph? So this is essentially related to the plot that we made for the variation of drag coefficient with Mach number for an airfoil, which was operating in the transonic regime. So this is typically the Mach number around which the significant changes in drag occur. And you may recall this discussion that we undertook for thick and comparatively thinner and optimized supercritical airfoils, what effect they have on the shock formation and consequent shockwave boundary layer interactions and their effect on drag, etc. So you notice that the drag went significantly higher for thicker airfoils which are not optimized for this kind of operation, and that led to severe interaction between shock and boundary layer, significant separation, large wake form, and consequent huge drag. So if you want to go into further details of analyzing this, then from a theoretical point of view, one may say that from linearized velocity potential equation. So you may recall that we had dealt with velocity potential equation in one of our lectures where we had kind of derived it completely. Now, when you try to simplify it under small perturbation assumptions, you get the linearized form. And when you deal with the linearized form in supersonic Mach numbers, it gives you a very interesting result that if you have a small flow inclination of a surface with respect to the free stream given by theta, then the pressure which is produced on that surface would be given by an expression like this, where this is a supersonic Mach number. When you go to subsonic Mach numbers, on the other hand, then you have an expression for pressure on a surface based on its incompressible pressure coefficient. So point to point, if you apply this equation, you would get the surface pressure coefficient based on the local surface inclination, while the equation number 2 can be applied to a body for which you already have the incompressible pressure coefficient distribution. And then from point to point, if you know that already, based on the local Mach number, you can comfortably calculate the Cp, which is compressibility correction included, so to say, in the sense that when the Mach number is not insignificantly low, then that accounts for the compressibility correction through what is called as the Prandtl-Glauert rule. So these are equations which are showing the effect of variation of Mach number both in the supersonic and subsonic regime. Now, if you look at these equations, you can get this idea that for supersonic flow, Cp decreases as m infinity increases. If you substitute larger values of m infinity here in the denominator, then Cp for a given theta will keep decreasing as m infinity increases. Now, this is in direct contrast with subsonic flow, where Cp increases as m infinity increases. So the two variations are shown here, and they seem to spike close to Mach number equal to 1. Again, the theory that we are talking about, which is based on small perturbations, doesn't remain valid if you move very close to Mach number equal to 1. But that the fact that the Cp is increasing significantly gives an indication that that would also have an effect on the lift or the drag that the body produces. And when we try to apply this theory to calculating lift and drag on a flat plate, for example, and here drag basically means wave drag, because we are operating within an inviscid flow perspective. So this is wave drag, and you get an expression which is again having a connection with first of all the angle of attack alpha at which the flat plate is inclined to the flow. The other is the Mach number, and as you can understand that as Mach number gets close enough to 1, there will be a significant increase in the drag here, and that is what is basically reflected in the figure that we looked at in the previous slide. So that is how you can explain it. The other part which I am leaving it to you to figure out is that what would happen to the wave structures as you operate at much higher Mach numbers. How would the wave structures on a typical airfoil look like, and compare them with how they look like when it is close to Mach 1. So that's a kind of a homework problem which will give you a complete picture. Next question from Venkat Narasimhan, perhaps I'm not having the complete name here. I have a question about what's happening in this video. So what's the question? In the example to calculate the section loss for diffuser, the velocity at the exit is taken by continuity, which made an implication that it's the static pressure that changes, or in other words, the loss is engulfed in static pressure changes. But I believe that the losses are imparted in dynamic terms. If I am wrong, please give an explanation. Okay, so let's try to address this question. This is interesting. Let's try to remember that the question that you are raising is, of course, with respect to the loss coefficients associated with different components of a wind tunnel. And let us say this is a subsonic wind tunnel. It could be open or closed circuit, really doesn't matter. Now, a certain component may be a constant area component, or it could be a variable area component. So if you are talking about the test section, it's broadly a constant area section. So if you neglect the blockage that is produced due to boundary layer displacement thickness, and because of the blockage, there could be a consequent acceleration, but that acceleration is not a very significant one. So if you neglect that, then the flow velocity remains constant by and large by the continuity equation, since we are assuming a constant density, that is a low speed wind tunnel. And therefore, dynamic pressure remains constant. Now, due to viscous losses, the static pressure changes and it reduces along the flow direction. And that's why in a closed circuit tunnel, in a later lecture, you would have seen that I have shown that how static pressure drops all around the circuit, and that is compensated by the static pressure rise across the fan. Now, stagnation or total pressure also reduces because it includes the effect of both dynamic and static pressure. Now, in an ideal situation of an inviscid flow, the static pressure would have remained constant. In this case, there would have been no losses, and dynamic pressure also remains constant because there is no change in velocity of the flow, and therefore the stagnation pressure would have remained the same. So that does not happen because you have viscous losses here. Now, it would have changed only if cross-sectional area was changing for internal flow or slope of the body was changing in external flow. So this is the only other possibility. For that, you have to go for changing the cross-section in case of internal flow, like in the case of internal components like nozzle or diffuser, or you are going to talk about external flow where the body shape changes. In that case, the dynamic pressure changes because the velocity changes inversely with area. So if there is a reduction in area, the velocity increases, the pressure decreases. The pressure decrease in that sense is the static one, and vice versa. So the static pressure also changes because if the area increases across the section, the static pressure also increases because the flow is diffusing, and vice versa. However, the stagnation pressure does not remain conserved. It reduces. This is because of viscous losses. It would have remained constant if the flow was inviscid. So if we do a detailed calculation, we would find out that there is an equivalent loss in static pressure too. That means what we are trying to convey finally is that whether it's a flow through a constant area section or a changing cross section in the case of internal components, which is the main area of interest here, then we'll always see that there would be a drop in the static pressure, which is by virtue of the viscous losses. And that is basically what we are addressing over here. So that basically will also reflect on the stagnation or total pressure, but the dynamic part basically works out in connection with the continuity equation. So as long as your area changes are happening, then continuity equation forces how velocity changes. And static pressure changes are dependent on both area changes as well as the viscous losses. That's how you have to understand the problem. Next question from Rajat. Two right or two left running characteristic lines can't intersect with each other. It would lead to second law of thermodynamics violation. Can you please explain why is it so? Any mathematical reasoning? Well, this is again an advanced question, but let's try to very briefly address it. I'm citing two situations here. One is that of an expansive wave. Later, I'll show you a compressive wave as well. So here we are talking about movement of flow from the left to the right, where you have a left state and a right state with the right state velocity higher than the left state velocity. And then if you try to draw the characteristic lines in the xt plane, then you will see that there would be an expansion fan opening up between the right and the left state, bridging the gap in the velocity. And the characteristic lines create a continuous fan which connects the two states and leaves no ambiguity of where each characteristic line originates. So at t equal to 0, you can always trace back the characteristics. No matter where you are in time, you can always go back and trace their origin at t equal to 0. Now, if you imagine that, well, this expansion fan did not arise, but you had a kind of a shock-like structure, a single discontinuous front from where the characteristics were emerging, so that you would still have the UL and UR states. Then what happens is you are actually trying to say that the characteristics emerge from the discontinuity. Now, this is a situation where you are not going to be able to trace back characteristics to their original states or the initial conditions. Characteristics emerge from the discontinuity. One immediate consequence of this situation is that there is no direct relationship between the characteristics and the initial conditions. Furthermore, the emergence of the characteristics from the discontinuity suggests that even minor changes or perturbations of the propagating discontinuity will alter the dynamics and therefore the solution. This is going to be an unstable solution. So this is an unlikely solution candidate. And this is not permitted in nature. It actually violates that entropy condition which we have been talking about. So we move on and we go to the compression case, and let's try to see what happens. To overcome the issue of non-uniqueness of the solution, we need criteria to determine whether a solution is admissible or not. And furthermore, we need to show that such criteria are sufficient to identify a unique physically relevant solution. And we refer to such a unique solution as the entropy solution. Now, when a characteristic can be traced back in time to the initial condition, if they have merged into a discontinuity, a shock, then this is the situation that occurs. So we are now talking about a compressive finite wave with the condition that UL is greater than UR. So this has a kind of step-like behavior which looks like this, where the velocities are moving towards the right and the left state is larger than the right state. So the left characteristics catch up, forming a shock. What if they intersect? Now, if they intersect, then crossing of characteristics of the same family would lead to non-unique properties, because each characteristic brings along with it properties associated with the flow field. Now, if they're crossing each other, then there are points where there are multiple values. It would not be possible to trace back a characteristic to its initial condition, like we discussed for the expansion case. Now, based on that, the consistent solution comes from what is called as the entropy condition, where the discontinuity basically propagates at a velocity which is an arithmetic average of the left and right states. And it is expressed through this, that UL is greater than the velocity of the shock, or the discontinuity is greater than the right state. And in a more formal way, it is stated through the lax entropy condition, which is in terms of the fluxes for all values of U which lie between the left and right states. Now, the notion of entropy is borrowed from thermodynamics, where this condition defines a direction of time by requiring that the entropy can only increase. So that's how, the concept of thermodynamics gets in, and we try to bring in the entropy condition in order to show that which gives us a consistent solution to such problems and which does not. Now, this is a advanced area. If you want to have more reading on this, you could refer to some of these references, which are very useful. Moving on to the next question from Sunil, where I hope I got your name correctly, because this was a last-minute question sometime in the afternoon today. So Sunil has queries about open source softwares for CFD, and then he has queries on depending upon whether the problem involves inviscid flow, compressible flow, etc. Are there separate modules to be selected and used? How involved these analyses are using softwares? Well, Sunil, the first part of your question, I would like to answer this way, that yes, fortunately, there are a lot of open source CFD softwares, and you are strongly encouraged to explore them. Some of the very well-known ones are OpenFOAM, SU2, and of course, many others which you can also explore. As far as the second part of your question is concerned, in order to get a firm idea about how you should be using a particular software, of course, there would be user manuals which you should thoroughly study before you actually try using the software, where, as you have mentioned correctly, that what kind of solution you are aiming for, what is the purpose of that solution that you are seeking, what application are you trying to find for that solution, etc. You have to be very careful about the problem definition. So these are the steps which I had briefly discussed in the CFD part of the course. So we have to be very careful about how we define the problem and what are the objectives for performing the simulations that we have set out to do. So once you define this, then you know that which modules to target, first of all, in the software. And then what are the options which are provided within that module have to be studied well. You have to make careful, decisions that how to go about choosing those schemes which may be available in order to solve the equations. You have learned about accuracy, you have learned about stability, how to use explicit and implicit schemes, how to choose time steps in order to ensure the stability when it comes to explicit schemes. Many aspects are involved where if you have a thorough understanding of the CFD basics, then you will be much better using the software which you are aiming to. That's what I would like to say. Additionally, you should also be careful about the grid generation, because a good quality mesh, a good quality grid will always help you get a better solution. And finally, it comes to post-processing. There are a lot of post-processing tools available. How best you should be using them in order to get the desired results also matters. That means a thorough understanding of the CFD aspects, like we did briefly through our course, or more extensive courses which you can follow, which are available in NPTEL as well. You can also refer to one of my earlier courses on Introduction to CFD for that matter, where detailed discussions have been done on these very important aspects of CFD. If you have a thorough understanding, you can very well use these softwares. You can understand the implications of each and every step that you are taking, so that ultimately you reach your desired goal. Rajat has a question. This is again related to, well, this is basically related to panel method. So that was one of the computational models that we discussed about in the computational part of the course. You may recall that vortex-based panel methods were discussed for lifting flows. So can you explain, with the help of small and short numerical, what values or distribution of vortex strength on the panel can be used on an airfoil, and what are the inputs required as a user once we write the code for this method? He wants to have a more detailed view. The second question that he has is, does the integral expression of induced velocity at point P due to the jth panel, how it comes and how it works out? Okay, let's try to address both the points. So I've just tried to put some screenshots here for the discussion. Now, if you recall that we have discretized the panel surfaces into straight line segments on which we have placed some discrete point vortices at the control points, at the centers of those panels, basically. And then you recall that basically, you have to solve the strengths of these point vortices that you are applying there. And finally, whatever pressure distribution comes up on the airfoil is going to be a function of those strengths. Each control point, when you choose and you try to calculate the pressure there, finally it is the strength of the vortex that lies there which will decide on the strength. Now collectively, you may recall that from the Kutajaukowski's theorem, we got an expression for the lift per unit span, and that had a connection with rho u infinity, rho infinity, and gamma. All right. So if you really want to have an assessment of what this total gamma strength should be like, one way of doing it could be that this is your lift per unit span figure, and then if you assume this to be a thin airfoil, from the thin airfoil theory, you can get an assessment of the lift for a given angle of attack. And from there, you can also get an assessment of what the total gamma should be like. And then you could, have an initial estimate of what kind of gamma values you may choose, so that you may actually end up having a total value of gamma like this, but that would be rather arbitrary. And this assumption would also not be required, because if you are trying to solve the problem as a system of linear algebraic equations that you want to solve for obtaining the values of gammas, such initial guesses ideally are not required. As you can recall, what you are trying to satisfy is that you are trying to satisfy net zero normal velocity at each one of the control points, and additionally want to solve the Kuta condition or satisfy the Kuta condition. And we already discussed that if you want to do all this, then it becomes an overdetermined problem. So one of those zero net normal velocity points have to be arbitrarily removed from the system of equations. So finally, once you are done with that, you have basically n algebraic equations to be solved. And that can be done with a lot of matrix solvers. So you can also use MATLAB, for example. So if you solve them, those system of equations, then automatically these solutions will come out. It's not required that you make some initial guesses. However, if you are planning to do some iterative calculations, then you can do it this way, as I explained, that you can have an initial guess of the gamma value, the total gamma value, and then try to distribute them in some manner over the surface as an initial guess, and then try to iterate the solution till you reach those conditions where you do satisfy the Kuta condition and the net zero normal velocity. But I guess that would be a laborious process. I would suggest that you take this approach of solving the n equations simultaneously. So this is the first part. The second part of the question was related to the normal component of velocity at each control point and Kuta condition satisfaction simultaneously would happen by defining this velocity potential, which is induced at a general point P due to the jth panel. And then we said that that is due to only one of the panels, while you have n number of them. And therefore, you would actually need to sum up on the n number of panels. So it's like saying that you have accounted for the effect of one of those point vortices, while you actually have to account for n of them. And that's why this summing is actually being done. So that's the answer to the second question. So with that, I have mostly addressed the questions that you have raised. So I'm not seeing questions coming from the chat window. So we are more or less done with the discussion. I would once again thank you for a very active participation in the course. And please continue to write to us, posting your questions from time to time. Prepare well on the upcoming lectures. I know that you are already into the experimental aerodynamics part of the course. So those lectures are currently being made available to you. So please make your questions available to us from time to time in the experimental aerodynamics sections. And while you revise the entire course content, if you have queries from the other sections which you have already done, you are most welcome to raise questions from those sections as well. So I would be very glad to answer them also from time to time. Prepare well for your end examination. I hope many of you would be actually appearing for the final exams. And in between, do your assignments carefully. If you are not able to follow certain aspects of the course, please write to us. We'll keep clarifying your doubts. So with that, I thank you once again, and we'll move closer to the end of this live session with the students of this course.